So, good morning to you, everybody. It's quite early, at least for me, being awake most of the night with children, but should be fine. So, I come from a slightly different field of physics. I've been doing plasma physics and general relativity for some time, and therefore I didn't know what kind of what level I would put this talk at. So it's quite tutorial. So if you find it too easygoing or so, I hope you will excuse me, because my intention was that everybody should have something out of this. So the title of the talk is Multifluids and Dynamo Theory in General Relativity. And I mean, here I could bombard you with equations, essentially, which there's quite a lot of. But I won't do that. I will show you some equations later. I will try to give you just a general flavor of what things look like when you impose general relativity in its full on dynamo theory. So the outline of my talk is that I will describe something concerning fluids and general relativity, and the importance of a covariant formalism, which is invariant under general transformations, and the way that you can split the space-time such that you get physically interpretable variables, and also a way to do perturbation theory without problems of spurious modes, etc. And then I will just briefly mention the multifluid system, which is the foundation of the MHD limit and dynamo theory. And then I will go into some specific examples. So, why should one look at general relativistic dynamo theory? Well, first of all, general relativity involves strong fields, large scales, or gravitational waves, for instance, or non-Newtonian effects, essentially. And these conditions under which they occur are also relevant at the same time as dynamo theory. So it's interesting to couple these two things together. I mean, there is quite some work done on this, but not in a general way. The main aspects of general relativity is that you have a dynamical space-time structure. So the fluid motion affects the space-time structure, and the space-time structure affects the fluid motion. I mean, even without fluids, general relativity is a non-linear theory. So it will give you non-linear effects, even though you have proper vacuum, so to say. The problem with general relativity, as most of you know, is that it's a very complex theory in the generic case. It consists of 10-second order nonlinear partial differential equations for the metric components, and in total there are more than 100,000 terms in these equations. And of course, you cannot treat this without assumption about symmetries or something like that, matter contents or something. You have to do some simplifying assumptions. But it would be nice, though, that even if you could do numerical calculations with very complicated sets of metrics, for instance, it would be nice if one could get a coherent and compact picture of general relativistic effects without dwelling too much on the details. So the main aim here is to develop a sort of general framework where we can look on a very large set of problems with the same theory, so to say. Because most of the time when people have been doing general relativistic dynamos and general relativistic fluid dynamics, they impose a certain metric, and then you do certain perturbations around this metric, and it's very restricted. You have to do one problem at a time, so to say. So you have to do the same work many times again. And the aim of this is to show that this is not really necessary. So the covariant formalism is, of course, essential for general relativity. And this was one of the main motivations for Einstein to deliver this theory of gravity. He wanted something which was independent of an observer, so to say. And if we want to go from proper general relativity to invoking fluid systems, you can either go from a kinetic model and covariant form like this with a collision. This is just a simple Boltzmann equation. You can do much more complicated things with the fully big GKY hierarchy and such things. And this will lead you to essentially energy momentum conservation equation where you have electromagnetic forces there. And this also follows from Einstein's equations.
What is GB? GB.
JB. Here. No, that's the 4 current. So this is the work done by the electromagnetic field on the fluid, so to say, this part. And then you of course have the electromagnetic interactions, which you can write in this form, where F hat here is the dual to this tensor. So it essentially involves an anti-symmetrization of this part. It's rather straightforward. So this is the Maxwell's equations with matter, and this is the ones that don't contain matter. And then, of course, you have to add Einstein's equations to this set of equations, which makes this quite a tremendous problem. And it's very nice to see that nowadays, actually, people can do fairly good numerical simulations invoking all of these things. I mean, MHD simulations in general relativistic backgrounds. So, in order to avoid dealing with all these indices and all these things, it's nice to make a splitting of space-time. And the way to do this is to introduce an observer. And an observer can be me and you, it could be a galaxy, it could be clusters of galaxies, it could be the fluid motion in a neutron star or something like that. And normally when you do a metric approach, you introduce a time coordinate which gives you a small time displacement dt, which is usually it's usually not a physical type of observable. But there's also a fluid velocity vector, which you can use as a time-like coordinate in some sense. It's not really a coordinate, but you can use it in that sense. And this depicts a very simple space-time, which is just a bit wobbly. So this is a hypersurface, and time goes like this up with the picture. If you have rotation in space-time, which means that, say you have a curved black hole or something like that, you will introduce a more complex structure of space-time. So the space-time itself will have a vorticity. And then you can also introduce a time-like coordinate, but it's more natural many times to follow the trajectories of the particles, like I've done here, with this curved path. The problem with that is that it's not hypersurface forming, so it won't form a hypersurface in a global sense. If you're just dealing with local physics, though, it's not a real big issue. So, the advantage, I said something about this previously, the advantage of doing such a splitting of space-time is that you get something which is easily interpreted. And you can deal with, for instance, electric and magnetic fields instead of the Faraday tensor, just as an example. You can also, it can be shown that you can do perturbation theory in these physical variables without having to worry about spurious modes, so-called gauge issues, which has been a problem in cosmology for a long time, but it was resolved by Bardeen using some very, very complicated variables, which is not easy to interpret in a physical sense. But I mean, you can build on that and you can introduce the same type of framework, but for these physical, easily interpretable variables like electric and magnetic fields. And also, for dynamo theory here, and this holds for many other systems, it allows for a very generic formulation of the problems you're interested in. And I think this is one of the main features, because you can get sort of an overview of what you could obtain from such equations. So what you do is you introduce an observer for velocity. And as I said, this can be galaxies or clusters of galaxies, or it could be some astrophysical fluid motion, like an accretion disk or whatever. It's just a preferred observer which you introduce. And then you can split all quantities with respect to the servers, with respect to this observer. So if you have something else moving past you with the velocity UA, you can split this into the gamma factor, just a relativistic gamma factor, this velocity, and then a three-dimensional part of this velocity, which is orthogonal to UA. You can introduce a projection tensor, which projects everything orthogonal to UA, which is essentially this. And then you can also take the covariant derivative, nabla A of this 4 velocity which you've introduced. And then you can split this into a scalar part, theta, a symmetric trace-free part here, which is the shear, the sigma, and vorticity, omega, and an acceleration AB. And these quantities are exactly what you would expect from sort of standard. If you have, say, a medium, then this would be the shear of the medium, this would be the vorticity in the medium. And so space-time appears to be as a medium. And AB here is essentially just gravitational acceleration.
This gamma is for the full velocity?
This is the one, this is the gamma factor you construct from this VA.
So you have to put it also in front of UV?
Yes, so this is you have to do something like, so you have to do something like this. Something like that. I mean, so you have to introduce this velocity VA, which I had in there, also in the gamma factor. So this is what it looks like. Thanks. Okay. Back to sleep. So this is just an explanation of all this. So when it comes to it's difficult to show a good picture of this because it's all in 4 dimensions. But theta here, it's just a normal Hubble expansion essentially, which you have in space-time. And this could be, for instance, the shear is typical for gravitational waves. Vorticity is typical for rotating objects, like rotating black holes. And this acceleration is, of course, just a proper gravitational acceleration. So what we do now, okay, we have this framework where we can split everything with respect to one observer, which is our interesting observer. And then we have fluids swooshing past this observer. So we have UA going straight like this, and then we have fluids which I denote by 1 and 2, in green and red, and they are swooshing past each other. And it could be electrons and ions, for instance. So they have each charge and a mass, and you split the velocity like this. And then you can introduce these splittings into Einstein's equations. And when you do so, you note that just when you do, as when you do a standard MHD theory, when you change the reference frame, you will introduce anisotropic pressures, for instance. And you will introduce heat flows or energy fluxes, which is due to the change of frame. And the same thing will happen here. So even if you start with the perfect fluid, even if each fluid here is the perfect fluid in its own frame, in this frame of UA, it won't be perfect fluid anymore. So you have to take into account those problems as well.
So you say, even tensors that used to be isotropic become non-isotropic?
Yes. I mean, because you change your reference frame. So if you, of course, if you sit in this frame, you won't see this 3 velocity, for instance. This VA will introduce this anisotropy.
Yeah.
And also, you have to include, it's quite dark here, but you might see these 2 arrows just to depict that there are other, I mean, now you have to add interactions between these 2 fluids as well, otherwise it's not interesting. So it can be electromagnetic interactions, it could be gravitational interactions, it could be the weak force, it could be anything which you would like. So this is, I mean, this could be neutrino fluids, for instance, neutrino-electron combinations as well. So that's why not why we're here. We don't want to do neutrino fluids at the moment, but you can take the MHD limit of this multi-fluid system, and then you can, of course, obtain a very nice dynamic theory. And what you will see in this system of equations is that you will have sort of a gravitational driving term and feedback as well in the magnetic dynamo, which is not difficult to comprehend because space-time affects fluid motion, of course, and so you would expect to have something like that. Also, you have collisions normally, so you have some viscosity in the fluid, for instance, and you will have finite conductivity sometimes. So this will give rise to the meter diffusion, but since this couples back to the gravitational field, you might expect also that gravitational degrees of freedom might be able to diffuse away through the matter and magnetic field diffusion. And if you have slow time scales, you just do the normal approximation. So you just look on ion motion and you neglect the inertia of the electrons. And then you can look on this ion electron plasma. I just want to underline that the MHD limit of a multi-fluid system need not be an electron-ion plasma. It can be any type of combination of particles. So it's not always that you can neglect the inertia for these. You can also introduce dust components, which means that you have impurities in the plasma, which is perhaps relevant for, say, supernova remnants. And then you will get ultra-low frequency modes in such systems through this MHD coupling. So what we do, okay, we form the average equations from a number of fluid systems. So we normally have two fluids, electrons and ions is most common, of course. And these systems, you have, of course, to do approximations here as well. So, for instance, if you look at cosmological scales, time scales and length scales, the resistivity is rather small, so you can actually use ideal MHD there. This is what people do anyway. I've seen quite recent claims that this is not a good approximation, but it might be actually true, but I'm not convinced yet. So at the moment, I think still it's quite a good approximation to use ideal MHD in cosmological settings. And then, as I said, you will have this frame-dependent energy fluxes and anisotropic pressures, which will introduce some new physics into the system. And, okay, the MHD limit in normal Newtonian physics gives you this equation for the magnetic field and this equation of motion for the fluid. Then you have an equation of state of the pressure. And here you have some viscosity term. Okay, so this is familiar to everybody. And then you add gravity. And then everything is crap. And anyway, as you can see, gravity adds quite a large number of complicating terms. And this is not all. First of all, you can see that first you will have some additional terms here in the fluid equation of motion. And this first term with a theta is just a Hubble expansion. So this is not a strange parameter in any sense. This is just gravitational acceleration, which is not strange either. It's just a new force compared to the pressure or anything like that. And then you will have some more complicated combinations of a shear tensor and
Coriolis force.
Yes. This is type of Coriolis force, but this is not from. Yeah, it's the analog of that because space-time is moving, so to say. So that's right.
Question, please.
So,
In the Newtonian limit, what terms would survive?
this would survive in principle because this is just a gravitational acceleration.
And that's what?
Sorry?
Above?
Above.
Yeah.
Let's see now. Theta, omega, that would vanish. This is just intrinsic curvature, so this would be flat.
And what is
it should all go away here.
Except maybe the last but one?
Yeah, exactly. I will show you. I have a undetermined function here, psi, which comes from. Normally when you derive this equation, you neglect the displacement current, and you can do the same thing here. But there are gravitational interactions in the equations where the displacement current occurs. So those are captured here, and they look like this.
E in this context is electric field.
Yes. So E and B, they all have their normal interpretation. E and B are the electric fields.
But what equation for electric field in this situation? How to
Well, yes, you have to introduce it either through Ohm's law or something else. I mean, so one of the Maxwell equations. So there's a feedback there. And this is, of course, one of the complications with these gravitational interactions, that you introduce the electric field in an unfortunate fashion. So it complicates things quite a lot when it comes to computations. And as I said, this term, which comes from the displacement current, you can't neglect, and it's quite complicated as well, as you see. Here you have, for instance, a gravitational wave effect coming in. And all these things look a bit annoying. I won't go into any details. This is just to show you that you can actually perform these calculations, put them in a very nice three-dimensional type of form, and you can have at least some kind of overview of what the terms will do. And I will show you some special cases of this. But it is complicated, and it gives you a feeling also why this is a difficult thing to simulate, even on very large parallel computers. So you have, I mean, the codes for doing such things is not really well developed yet when you introduce these kind of interactions. But it would be interesting to see if you can actually do that in the future.
So can you maybe summarize the restrictions that you are left with in terms of the metric, for example? What are the restrictions here?
There are no restrictions on the metric here.
Uh-huh.
This is completely general. This is all general relativistic effects in the dynamo you can have.
Mm-hmm. But it's given, so you of course haven't solved for the metric as...
Exactly. So this is, either you can look on this as, okay, you have a fluid, you have an MHD fluid immersed in a given space-time, and this gives you sources, like A and theta and all these things. They give you sourcing in the equations. Or you may do it self-consistently.
Mm-hmm.
And this is the difficult thing, because then you have to solve Einstein's equations.
The frame dragging effect is on the previous equation, a previous page, of course, only. So can you maybe show this?
Well, essentially, this Coriolis force here is a frame dragging effect. So.
Yeah, but in the B equation, you must also have one.
Yes, I mean, there are, here you have one omega cross B dot, for instance. There is a B cross omega here, which gives you frame dragging effects as well.
Must be a gradient. Anyway, doesn't matter.
This,
what?
The equality sign probably is an addition or what? Because
sorry, what do you say? Sorry.
That equality sign, oh, okay, fine, that's fine.
Yeah.
And if you go to either going to zero limit,
yes,
the ideal limit,
yes, I will show you.
These terms will go
yes,
away,
yes. So I will show you this as an example here. So the ideal MHD equation looks like this, and this has been used quite a lot, especially if you remove all the anisotropic terms like acceleration, vorticity, and shear. Then you're just left with this expanding universe parameter, the Hubble parameter. So this is just, I mean, you all know what this does. This just dilutes the magnetic field as it expands. And if you keep the finite conductivity in this equation, but you look at the isotropic space-time and not homogeneous essentially. Yes, homogeneous in the magnetic, in the space-time structure, but not in the magnetic field. So you look on expansion and collapse scenarios. You will get these expansion terms just like you have here, but you will also have some terms due to finite conductivity here, which will introduce further damping of these modes due to the expansion. And this is a curvature term which tells you just that space-time is not flat on its hypersurfaces. And if you look on a space-time which is very close to flat, but it has a small vorticity, you see that this is the vorticity contributions to this equation, the dynamic equation. So there are some interesting effects here as well, but this is not, due to the fact that space-time vorticity is very complicated from a, I would say from a intuitive perspective, so to say. It has not been dealt with very much. You can actually, I mean, what you could do is you could look at an exact solution to Einstein's equations, which has a given vorticity, and you can calculate what it gives for this MHD dynamo equation.
Here you have assumed a flat FRW metric, or?
Sorry. Yes. Here
you
is.
have an open universe. then you get extra terms?
Yes, yes, you will get extra terms. And I also dropped some nonlinear terms here in terms of the vorticity, so there, because it was very ugly. So this is just if you have a slowly rotating space-time for some time. We have been looking some on the possibility of having gravitational wave interactions with plasmas and the way it may show in the effect it will have on signatures of gravitational radiation. And one thing you can do, for instance, with these equations is that you put a magnetic field, constant magnetic field like this, and you drive a gravitational wave through this from, say, a binary system or something of that sort, or it might be a pulse from a supernova. And you will have then two outgoing waves, one Alfvén wave and one gravitational wave typically. This is just showing the polarization of gravitational waves. And this will, of course, this is sort of a linear decay process which I depicted. You can do this non-linear, so you have a backscattering as well, and you will produce some residual gravitational waves floating around in this NHD plasma. In essence, what it shows is that, especially if you have finite conductivity in these systems, you might have a sort of turbulent mixing of these gravitational waves, and the signal will be changed from binary systems, for instance, due to this. However, it's a very weakly interacting particle, the graviton. So you wouldn't expect to see it with today's accuracy. So you would actually have, if you wanted to, as a probe of astrophysical environments, you will have to further develop the accuracy of such systems, such detection systems, like the interferometers.
If you look at a very simple situation in which you have a magnetic field, and it's just like you showed, but wouldn't you expect waves which are a combination of Alfvén and gravitational waves?
Exactly, yes.
So they're mixed.
Yes, that's absolutely right. You will get such combinations. And, I mean, if you look on the equations in its full, I mean, at a non-linear level, you can see that you will have a parametric exchange of energy between Alfvén modes and gravitational wave modes. So you can do some simulations of such simple systems and see how the energy is transferred.
I mean, even in the linear limit. You just look at linear waves.
Yes, the problem is that in the linear limit, the magnetic field only couples quadratically to gravity. So, because the B square enters into the energy momentum transfer. So you could do some sort of 1.5 order type of perturbation theory and obtain such results, I should say.
How strong have the fields to be in order to get any effect?
Oh.
Is there that gravity has to be produce as strong deformation of the metric as the gravitational waves or something like that?
So
in order to get this, say, some substantial scattering.
Yes.
Say 50% or something like
Yes.
that. How strong have the fields to be?
Okay. I would say that the magnetic field here would probably have to be in the magnetar range. Magnetar. So it's 10 to the 15 Gauss or something like that. Because this, I mean, the coupling parameter is proportional to Newton's constant, of course, over c to the power 4. So it's a very small one. And this is, of course, the problem with gravitational wave detection in general. So, I mean, this is more a prospect for the future, that if you improve the detectors, you could actually see some of these effects. And I mean, it could be also a probe of magnetic field strength in that sense, I mean, an independent probe of it. But at this stage, I would say that this is just model calculations. One has to take them for what they are. And this is an indication of how difficult it is to do something with this. And I mean, gravitational waves is only one source, of course. If you have really strong gravity, proper strong gravity, of which we really don't have any proper tests in general relativity yet, this could be a nice way to probe it indirectly through other types of electromagnetic radiation. Okay. So the conclusions here would be that from this system of equations you could develop, for instance, numerical codes which are adaptable to many types of, at least generically, or I mean hopefully you could say, adaptable to many types of geometries and gravitational situations. And also you could compare what is known from perturbation theory with numerical results. It would be interesting to see if you can do accurate numerical calculations of these kind of things and compare them with very accurate observations which you have now from WMAP and these kind of facilities. And examples of questions you might ask here is, for instance, is there a significant damping of gravitational waves, which is unexpected, nonlinear regimes perhaps? So can you diffuse the gravitational degrees of freedom in general due to magnetic diffusion, say? Could you get some gravitational wave bounds perhaps? This is sort of the questions you might ask from these kind of equations which I've shown today. So, thank you.
Thank you very much. We've had quite a few questions. Any more? Yes, please.
I would guess that an interesting area for applying such a formalism would be dynamo effects at a paired black hole.
Yes.
Throwing in some magnetized plasma, weakly-magnetized plasma into a paired black hole and see what gravity does.
Yes.
We expect that there happens much more than the shear terms already do. If you go through all the terms.
I wouldn't think so actually, because I mean, if it's a very rapidly rotating black hole, perhaps that has a significant dragging of frames. But for a very large rotating black hole, which rotates slowly, for instance, I don't think you would see that much of a difference. That's my prediction anyway. So I would like to stress that this is, I mean, these kind of things which I'm talking about is, first of all, it's interesting with strong field gravitational effects because we have no probes of them as yet. But I mean, things which are close in the future is high precision measurements of weak effects, as it looks at the moment.
Just following up on this question about Kerr black holes, of course, there is in connection with this frame dragging effect, you have this winding up of a poloidal magnetic field, which turns into a toroidal magnetic field, which is one part of the dynamo cycle. But you also have the winding up of a poloidal electric field into a toroidal electric field, which then would complete the dynamo cycle.
Yes.
And that has been discussed some 15 years ago, and particular solutions that have been presented were not correct back then.
Okay.
But in general, the question remains still open, but that could work.
But it's a very good remark, because I think this is one of the things one can note from this. I took some, on this conclusion section, I talked some of what you might do. And one of the things I didn't mention is that you might use this general, fairly compact framework in order to analyze well-known results again, so to say.
Yes.
From dynamo theory.
So it's about the numerical codes, and you showed us the equations got a bit more difficult. What about boundary conditions?
Yes. This is also an issue because, do you have periodic boundary conditions, or,
I can see if you impose your metric, you might be able to do.
Yeah.
But if you want to solve self-consistent metric, what do you do?
Well, it's a good question, because I'm not an expert, so I don't know. So this is for someone else.
Okay, let's thank Matthias again
Okay. You know, let's go.
Do you want an introduction?
Yeah, I'm not sure.
Okay.
Good morning, gentlemen.
The next speaker needs no introduction.
Yes, of course. No, for sure. My name is Nathan Krivolin from Ben Gurion University, and I tried to came back from this very interesting question about relativistic fluid mechanics, normal fluid mechanics, and even to fluid laboratory. So in some sense, I prefer to give my talk in a little bit more general context that it was, something happened. I see, okay. Something happened. It's a little bit more general context that we discussed. Okay, I've got some problem. Okay, just a moment, please. Okay, what happened with some electrical problem? Okay, no, it's not. What's happened with? Okay. Okay, maybe we'll try again. I apologize.
Who's the next speaker?
Yes, I hope it will be okay.
Okay. Okay, Julian.
Yes, it's
okay, yeah?
it's a problem. Yes, it's some problem with computer. Okay, but maybe you've got actually maybe you've got my flash memory.
Sure.
Okay, so it is something happened. Yes, it's a problem. You're right. You're right. Yeah. So actually, what happened? Okay. No. Oh, that's all. That's okay. Movie, two movies. Two movies. I'm really sorry. You know, let us start. I will discuss in this talk, my apologies for some delay. From one hand, convection in more wide content sense, astrophysical and meteorological convection, symbol will demonstrate how close to each other, and laboratory convection. And we can imagine laboratory all features and understand very interesting details, sometimes unpredictable, at least for us. And for example, some general opinions, what we find sometimes, plainly speaking, wrong. For example, what we demonstrate that you can organize from one hand turbulent thermal flux, for the other hand practically zero gradient of temperature. And it's matter of experimental factor. And how it influences on the problem of generation of magnetic structure in turbulent media. It may be, how to say, very interesting in some sense, unpredictable. Okay, so topic of my presentation, as you see, is formation of large-scale inhomogeneous magnetic structure in turbulent convection. And you can see three examples of convection. First is laboratory with sufficiently low Rayleigh number. It is just silicon oil. This is cloud convection. It is so similar, solar convection, practically no difference. So, and this work was done with my, how to say, with my old collaborator, more than 20 years working together, Igor Rogachevsky, but because we will study some meteorological phenomena and discuss and laboratory experiments. Of course, another people were involved in this activity. This Professor Elperin, Professor Edelman, and our PhD students, Alex Green, Henry Markovich, Itzhak Sapir-Katera, he is now our PhD student too, and Ilya Golovev, now he's finished his PhD. Oh, and another very crucial person, Professor Zoltankevich, from University of Helsinki, Finland. Before he was chair of meteorology in Uppsala University many years in Sweden. Okay, so this is outline of my presentation. A little bit, how to say, ambition. Maybe I haven't enough time to mention all these topics, but I will try at least. Again, this is the same pictures. A little bit amazing how this different convection so similar each other. But in this very nice, how to say, incoherent picture, we've got immediately very strange problem. If we compare depth of the structure and horizontal size, roughly speaking, this ratio 1 divided by 2. It widened two times than the depth. But if you take convective cells in nature, I mean in turbulent, real turbulent situation, it is known that this ratio just 1 divided by 4. And in some sense it's open question, and if you ask meteorological guys why it is true, the answer I don't know. And it is first, how to say, cloud of this very nice picture that all convection is the same. So this turbulent convection, laminar is not the same. But of course, if we speak about solar situation, we should take into account magnetic field. It is nice and famous picture, solar granulation with sunspots, with activity region, and so. And it's another story, but of course it's possible to take into account. And in atmosphere, we've got nice possibility to measure directly velocity. This you can see velocities and temperature, or difference in temperature. And we see cross section of convective cell. It is enough light, it's just a small part, central part. And what's interesting, precisely the same picture we find in average in our laboratory. Practically the same structure of temperature, practically the same structure of motion. It's a picture from our laboratory. So in this sense, all nice. Look, let us discuss briefly equations. It's obvious that we should take first of all equation of motion, Navier-Stokes equation, with many familiar forces, pressure, gravity, Coriolis force if we speak about star or planets, and viscous storms. If we discuss convection, we should take into account transport of thermal energy, and if it needs continuity equation. No, I just in order to remember that we've got 3 plus 3 independent parameter, pressure, temperature, density, and 3 component of velocity, but just 3 plus 5 equation of motion. And we should add equation of state in order to close the system. All this trivial, of course. If we try to involve plasma or in general conductive fluids, we should add induction equation and take into account electric conductivity. Okay, next important step, so-called Boussinesq approximation. The idea is to combine together these 2 terms and take into account equation of state. If we will do it, we can get so-called Boussinesq approximation that we replaced terms with pressure and with gravity force by buoyancy force, buoyancy term, which is actually proportional to so-called potential or superadiabatic temperature. And in this situation, the equation is much more simple. And of course, if we speak about magnetic field, about conductive fluid, we should add magnetic force. Part of this force is possible to take into account by total pressure, but some contribution which is said with magnetic tension and with contribution of inhomogeneity of density, we should take into account as magnetic force. Okay. The next step, because we try to study turbulent phenomena and take averaging equation. And I can imagine that many people in this audience can say, okay, that's old story, nothing new. We don't observe at all any average parameter, but it's not so true. We will demonstrate it. No, this standard Reynolds decomposition, fluctuation and average part. After averaging, we will get very similar equation. What's in use is just effective stress tensor, which take into account turbulent stress, Reynolds stress, magnetic turbulent stress, and contribution, regular contribution of mean magnetic field and contribution of turbulent magnetic pressure. And of course we should take into account induction equation, it's standard term, but because we took into account gradient of density, we got a divergence term in an elastic approximation that's proportional to velocity. It is a very important term in view of instability that we should study. Okay, but before all this discussion about magnetic field, let us look more general on this system. If we take these 2 equations, equation for temperature and equation for velocity, we will describe convection. If we will take these 2 equations for equation of motion and for magnetic field, we will describe formation of magnetic structure. So in some sense, magnetic field play a role of buoyancy. We will demonstrate it in the next slide. Okay, so interesting possibility before study magnetic phenomena to study in laboratory what actually happened with convection. And let us discuss a little bit our experimental result. because it's non-linear, very complicated equation, difficult to predict results. Okay, what we have got? In our laboratory we have got experimental set. It's very simple, it's just box. Box with wide 52 centimeters and height 26 centimeters. So small box. But nevertheless, we imposed large temperature gradient. Difference in temperature, several tens Celsius or Kelvins, better to say. So-called Rayleigh number, we will discuss immediately, in our situation really large, 10 to the 8. So we really observe turbulent convection. What actually we observe? It is our experimental set. You can see this box. We can to heat down wall and to and we've got cold water on the upper wall. As a result, we produced very nice convection, and we've got laser optic, which, strictly speaking, is just source of light, of laser sheet, and we put in this box small seeding particle is charged incense, the best incense, by the way, from Orthodox Church of Jerusalem. We checked it, and by this camera we can calculate velocity in many points, so we can build simple field of velocity. And what's the result? This is instantaneous picture of convection. Many small vortexes. If you know that it's convection, you can say, I can observe something on the periphery, which is similar to cells. It is instantaneous picture. After that, we took 150 of these pictures and just evidence. And what's the result? The result is very interesting. It is what demonstrates this picture. Demonstrates very well that really we have got large scale phenomena. This picture is very stable. It maybe exists many hours. And pay attention that just in the periphery we can observe small eddies. We observe just one large eddy and no small scale details. It means that we've got good scale separation. We checked it by special way, but nevertheless, for this first point of view, it's obvious that we have good scale separation. Roughly speaking, typical eddies in this situation it is several centimeters, while our general picture has a ratio 1 divided by 2. And by the way, if we build from these vortices hexagonal structure, the ratio of depth and the diameter will be approximately 1 divided by 4. Precisely as we observe in nature. Okay, no, it is standard Boussinesq approximation, and it is normal idea to use just old equation, take Boussinesq approximation, take Rayleigh model, and try to calculate. Of course, we have got something new, but what is new? New, it is just effective parameter, effective viscosity, and effective diffusion of temperature, nothing else new. But fortunately, we have got possibility simple to measure in this situation velocities. And we made it. It is our experimental parameter. Pay attention, please. We know that the integral scale, we just find it, just 4 centimeters. Less than 4 centimeters, 2 or 4 centimeters. Typical velocity, turbulent velocity, 6-10 centimeters per second. We can calculate, of course, effective parameter. Difference in temperature in main part of of turbulence. Just several degrees, maybe 1, but maximum say 35. Less in reality, but take this one. It's definitely our estimation. And after that we can just find normal Rayleigh number. It's huge. But if we calculate effectively Rayleigh number, we find that it's very small. Small, that's critical. So in some sense, picture which we observe cannot exist at all. How it exists? Good question.
So delta, that's based on the delta T of the convective state.
Yeah, yeah. Yeah, so it's a little bit strange. Agree.
It's less than 6,000, you mean? 6,000 you would expect?
It's 6,000, no, I will demonstrate in our case, as we've got some anisotropy. It will be even more. It's next step. Okay. So, it is just, how to say, I would like to remember to you what does it mean, classical Rayleigh theory. Rayleigh theory, it says that we have got critical Rayleigh number as function of ratio between vertical and horizontal structure. And this is for rigid body, rigid condition, this is for free condition, and in any case, our effective Rayleigh less than these two parameters. So, but what important, we believe that thermal flux just this simple parameterization. We study this question very carefully and simple calculate this correlator in the spirit of dynamo theory. And what we find first that we've got what we name Kolmogorov-like flux, and we've got traditional contribution, but together this we've got non-traditional contribution. This is so-called Derdor storm, which people paid attention to this storm approximately 30 years ago. What's important? The direction of this storm in any situation upward. As a result, if fluctuation of temperature enough large, it's possible that all vertical flux will be provided by just this storm. In this situation, so gradient maybe really tends to 0. So it is really something new. People knew about this storm many years, but if you open any standard book, never took into account in calculation, say, of convective zone. An additional thing, if we've got this flux, this basic flux, if you like, we've got some additional processes, redistribution of flux. What actually happened? If we've got some thermic or several thermics which go up, difference between molecular transport and turbulent transport, that local Coriolis forces and inertial forces influence on these thermics. As a result, it's possible to concentrate these thermics, to change direction, and so on and so on. And all these terms, new terms, describe this phenomenon. This is, how to say, illustration of first term, which is proportional to divergence of horizontal flux. Let me impose some cell, which converges in horizontal direction. Of course, the initial homogeneous flux will be concentrated. We produce hot spot in this place. This hot spot will be source of buoyancy force, and we increase our cell again. It's some instability which we find approximately 8 years ago together with Igor and Sergei Zeleznikevich. As a result of calculation without boundary condition. And what we find is that we need scale separation. First of all, the scale of structure is the scale of turbulence. We need scale separation at least 10 in order to produce some generation. And what's the important point is the ratio between vertical and horizontal scale much more close to 1 comparison with the old Rayleigh theory. Much close to half. So it means that it's really what we observe. LZ equal 1 and horizontal scale equal 2. We'll study more carefully this question. We take into account all related terms. This is all related terms and our new term. And if difference of temperature it tends to 0, our term more important. And the parameter which influence of this stuff, it's mu. If zeta tends to 0, mu tends to infinity, this term very important. And we calculate again this stability diagram for mu equals 0 but anisotropic turbulent transport. And we find that in this situation critical Rayleigh number larger than standard. And after that we take mu equal 5, it means say the difference in temperature 1 degree or so, 2 degree in our situation. And we find that the critical Rayleigh number will be 98 just. So in this situation, excitation of this structure much more simple than the standard. 5 minutes? Okay. And you can observe that we find that the ratio equal 0.5, then for standard situation close to 1. So the difference between our theory and Rayleigh theory, first of all, it's form of cell. In our situation, it's 1 divided by 2. In Rayleigh theory, 1 divided by 1. It's totally different. And we normally observe in our laboratory durable convention, you observe this picture. And this is our averaging. And this is a very interesting example. This is instantaneous pictures. Again, after extracting average velocity, or just instantaneous? Instantaneous. So, no side, and the left side is the result of averaging. Amazing. And what's more interesting, level of velocity practically the same in these two pictures. Okay. Again, experimental parameter. Again, but now we don't understand what actually happened. Our critical Rayleigh number less than 100 in realistic situation, so no problem. But what main lesson that we studied, that practically in this situation, in turbulent convection, in average, we've got very homogeneous in vertical direction temperature, practically isothermic. And in order to study more carefully, we built another device. We add two grids, two oscillating grids. And what's interesting, this picture without which grids doesn't work. It is a familiar picture, but if grids work, we destroyed these two hot regions, and we produce practically horizontal homogeneous temperature. But more important, we produce normal gradient of temperature. This is gradient of temperature in two-real convective situation, practically zero. And this is gradient of temperature when grids work. And this is really interesting, I guess. Now, this is some references that you find. Okay, let us discuss now magnetic phenomena. The question is how to average this equation, how to find this. It is a long story. I would like just to give you results. What we find that we can split this effective stress tensor into part magnetic and hydrodynamic. The dynamic is more or less familiar. It is similar to turbulent viscosity with some additional term, which is a second turbulent viscosity, if it's compressible situation. And we've got two contributions: effective magnetic pressure, which may be negative even, effective stress, which can be negative too, and something additional, which is proportional to thermal flux. So specific convection contribution. Of course, QSEQP depends on convection too. It depends on velocity field, but in addition to convection. This is effect of negative magnetic pressure. It could be which influence on the level of magnetic pressure. It's very large for small magnetic field. It's logarithm Reynolds, as we discussed yesterday. And this is a result for magnetic pressure. Interesting, we've got some negative part. So, in simple words, we can organize equilibrium between zero magnetic field and something non-zero, so cube. Yeah, this one. It's not so large, but serious. Okay. And the same for stress, and the same for anisotropy. And now it's equation which we solved in order to reproduce magnetic structure. We have got two equations. First equation of motion, and second induction equation that we take into account just turbulent diffusion. For instability responsible, roughly speaking, these two terms. If we drop all terms and take into account just these two, we will see immediately that if QP equal 1, it's just Parker mode. But if if QP is negative, in this situation, instability is possible even in homogeneous magnetic, in a totally homogeneous magnetic field. This is a result of this calculation, instability, and for this line is purely hydrodynamic case, and thick, thin, dash dotted, and dash dotted thin, it's several cases for convective situation. Pay attention that the gamma in the convective case is much larger. By the way, and we've got threshold for purely hydrodynamic situation. Roughly speaking, 0.3 something, maybe less even. And the reason, maybe explanation why we observe magnetic structures as sunspot in solar situation and don't observe in galaxies. We found convection in galaxies, as I know. And of course, we, together with this growth, we've got oscillation. And we discussed yesterday what actually happened. Of course, by parts we calculate magnetic fluctuation, which result of technique of large-scale magnetic field. And we really observe that for very small magnetic fields, the amplification very strong. Roughly speaking, 25 to some. It's for magnetic resonance number 10 to the 6. But when we're close to equipartition, this amplification close to 1, even less. This is purely hydrodynamic case. This is two cases of convection.